So last lesson, we were talking about using recurrence relationships to model growth and decay, but what sort of relationships were we using them with? Starts with an A.
Where does it have that?
Arithmetic. And it should also be on the one that you just got. Geometric growth and decay.
Okay, sorry, it was the other way around. I'm very confused.
Okay, so let's concentrate, girls. So last lesson we were talking about arithmetic sequences. Today we're talking about geometric sequences. So we're talking about things that we're multiplying by. So we have geometric growth and decay is when a value increases or decreases by the same percentage at regular intervals. When we're talking about depreciation, which means going down, decreasing, it is also known as balance depreciation. Doing the same things, but instead of doing arithmetic sequences, we're doing geometric sequences. We're talking about growth and decay. Alright, I'm just going to move down a bit. So we've just got a fair few examples to go through and how we use geometric growth and decay. And hopefully the examples will help us make sense. So the following recurrence relation can be used to model a compound interest investment of $1,000 paying interest at the rate of 8% per year. So remember when we talked about, so thinking back to chapter 4, when we talked about financial maths and we talked about compound and simple interest, when we graphed simple interest, what did it look like? What sort of graph was it? Sorry? Yeah, it was linear, yes. So when we had a simple interest graph, it was linear because we were just adding the same amount every single time because everything was calculated on the first amount. When we did compound interest, what did it look like? It looked curved because we were calculating everything on the amount before. So if we were talking about simple interest, what sort of sequence is this? Yep, it's arithmetic because it is linear. And what sort of sequence is this? Geometric. So that's how we can see the relation between simple interest and compound interest and their patterns. So simple interest is an arithmetic pattern and compound interest is a geometric pattern. Alright, so if we're talking about compound interest, we know we must be talking about a geometric. Yep, a geometric. So we know we're talking about geometric, so we know we're going to be multiplying. Okay, so we're starting with $1,000 with an interest rate of 8% per year. Now, last lesson we talked about this V0. What did this mean? What did the V0 mean?
Before, like, the start of the year.
At the very, very start. So we haven't actually done anything. We haven't performed any calculations. This is what we're started with. Once we get to V1, what does V1 tell us? Yep, so at the end of the first year. Right, so 0 is at the very, very start. 1 is at the end. Okay, so where did we get this 1.08 from? Yep, 8% of 1,000. And why has it got a 1 in front? What would happen if I multiplied by something by 0.08? It would get smaller. But we're told that we're increasing, so what do I have to have? I have to have a number bigger than 1. Does that make sense? If I didn't have that 1 in front, my numbers would start to decrease. So if we're increasing, we always have to have a 1 in front of the decimal, at least a 1. Okay, so in the recurrence relation, Vn is the value of the investment after n years. So use the recurrence relation to find the value of the investment after 1, 2, and 3 years. So we know that our V0 is 1,000 and our V1 we're going to start with using our equation, Vn plus 1, 1.08 Vn. What's my n going to be? That I'm going to sub in.
0.
0. Why is it going to be 0?
That's just what we're like.
Yep. Good, because it's the previous one that we've used. So V0 plus 1, 1.08 by V0. So V1 is going to equal 1.08 times 1,000 because that's what my V0 equals. So at the end of year 1, put that into my calculator, I'm going to have $1,080. Any questions about that? All good? I'll take that as a yes. All right, so that's after 1 year. After 2 years, so to find after 2 years, put in my equation again. What n am I going to use?
1.
Why 1? Yep, good, because it's a previous term. So 1 plus 1, 1.08 times V1. 1 plus 1 is 2. And my V1 was 1,080. So I'm putting 1.08 times 1,080 into my calculator. And I get $1,160.40. Any questions? All right, so we've got our 1 year after 2 years. Now we need to find after 3 years. So start with my equation. And again, I'm just copying that straight off there. What is my n going to be for this one? 2. Why is it 2?
It's the previous term.
Because it's the previous term. Excellent. My V2 was... What was my V2? Good. So my V3, I put my 108 times 1,160 and 40 cents into my calculator. And I end up with $1,1259.71. It doesn't tell me to round to the nearest dollar or anything like that, so we're just going to round to the nearest cent.
If you don't put the first bit, so you kind of just put a V2 plus 1, will you get a marker?
If you forget that bit and go straight to there, that'll be fine.
Okay.
Yeah, that's fine.
Do we need to do it like the first one to show that?
Do it for the first one, but then for the rest of them, yeah. Because if you do it for the first one and then you've mucked up, at least you'll still get the marks because you've shown
Yeah.
that you've used the right relation.
Yeah.
Okay, so when will the investment first exceed $15,000? No, not 15,000, 1,500. So we're just going to do this via our calculator. So we're starting at 1,000. And what are we multiplying by?
1.0.
Yep, and we're just going to keep multiplying by 1.08 until we get past what?
1,000.
Yep, until we get past 1,500. So let's have a go at that on your calculator. And what do we get to? Count how many times you do it. So we know it's going to be more than 3 years because our 3 isn't up there yet. today? 6. You are a spud. 6? Who else got 6? Well, everyone else get 6? 6 looks pretty good then. So after 6 years, the investment will exceed $1,500 in value.
Is 6 years when it's 1,500 though? Doesn't it have to get higher? Doesn't exceed mean like?
Yep, so once it gets to that.
What's
Yeah.
1,596?
Oh.
Yeah. Any questions about that last bit? All good? Wonderful. Alright, anyone still copying that? Can I move down? We're all really quiet today. Tired.
Basically.
How was everyone's day off?
Yeah.
I need that every week.
I
I would love it every week.
I did that.
More depressed though. Because I just have to like go through like Monday again.
But then you only get to Wednesday and it'll be the
But
weekend.
then we have tomorrow.
Yeah, true.
Do you have tomorrow off?
We have an excursion to the city.
Oh,
So maybe we don't have to do any thinking. We're just getting lunch.
a bit of snoozing, that corner. Yes.
Do you have eight like self-collection?
We have to get there.
That would be on Monday.
So 8H, so you should have the first part of it.
But then I can't cut it out.
Oh, so you want another page? Yeah. Can you pass that back?
And like I was only like.
Alright, let's continue to concentrate. Alright, girls. So a car is purchased for $18,500. The following recurrence relation can be used to model the car's value as it depreciates by 10% of its value each year. So this is our recurrence relation. We've got a 0 because
It's the start.
that's the start. It's not at the end of a year. It's the start, what we're starting with. And why have we got 0.9? Where did that come from?
Because it's depreciating by 10%.
Yep, good. So that is 10% of 18,500, and it doesn't have a 1 in front of the decimal place because
It's going
it's depreciating. It's going down. So we need our value to be smaller than 1.
in a way, it's not really 10% of 1,000. I mean, 18,000 is 90% of that.
In a way, yes, absolutely.
Is that's why it's 0.9.
Yes.
That's why the other one is like 100 and.
Yes.
Is this what I did yesterday?
Possibly, but we were using arithmetic.
Do we?
Yeah.
So we would no. So this one we're going down by it's been calculated on each new value, whereas the one before it was just going down every time it went down by $500. So does that make sense? Whereas this one, it's going down by 10% of the value of now. Then the next time, 10% of the previous value, then 10% of the previous value.
But are we figuring it out first time?
No, different because
Because you're timesing here.
yes.
And you're not plussing. Like, so
Oh,
you're
yeah.
timing-
Yeah, so the other one we're talking about adding and subtracting. This one we're talking about multiplying. Yes.
Do we ever have to like find the rate like by ourselves? Like,
If you do,
yeah.
times 10 over 100.
Yeah. So like they'll always like give us the rate though.
Yes.
Yeah.
Yep. Okay, so use the recurrence relation to find the value of the investment after 1, 2, and 3 years. So, you know our V0 is 18,500. And that's just our formula. So to find after the first year, What am I going to sub into my ends? As my ends. Yep. You need to write this part out. You need to show where you're getting your numbers from. You ask me this every lesson.
Oh, my mom. So every single time I try to do it by myself, I do it wrong.
Why does V1 equal
Why does V1 equal that? Okay,
Ah,
so-
sorry.
Oh, yeah, boy, I didn't do it wrong.
My mistake.
Yeah, boy.
That should be 1. Sorry, 0.
Are you angry as well?
I know. I'm really sad.
No, you can't be sad, you have to be angry.
Does that make sense? All good, Ruby?
Yeah. Do you have to do it for like 1, 2, and 3 years, like the same thing?
Yeah. You can skip.
Does that say V0 at the end?
Yes.
Okay.
You can skip. The first time you need to put that in. Then if you want to skip that one the next time, because it's just a formula, that's okay. But you need to show where your numbers are coming from. Okay, so we now have 0.9 times 18,500.
But why? If it was arithmetic, would we be adding this is 8 0.9?
We would be taking away whatever value 0.9 is of 18,500.
Where did I get H?
Does that make sense? So because we're taking away 10%, so we're trying to find out, okay, what is 90%? That's why it's 0.9. We're trying to find what is 90% of 18,500. Then what's 90% of 16,650? Whereas when we're taking away, we first have to find out what is 90% of that, and then we just take that value away every single time. Does that make sense? So we would be finding out that, yeah, whatever 90% is, and then whatever 10% is, and then taking away 10%. But just that one number every single time, that's the difference.
And that's an arithmetic.
That's arithmetic. Yeah. Does that make sense?
Yeah.
Okay, cool.
So with geometric, it's always going to be less than 1, the value.
If we're depreciating, if we're decaying, yeah. Okay, so then our V2 is our Vn plus 1. What am I up to? 0.9 Vn. So when you're saying do I have to write all of it, this is the one you can skip if you want. Alright, but you need to write the 1 plus 1, 0.9 times V1, because you need to be able to show where your numbers come from. And then when will the value of the car first be worth less than $10,000? So starting with 18,500, what are we going to multiply by? Yep, 0.9. Multiply by 0.9 by 0.9 until we get under 10,000. So how long does that take?
6 years.
Yep, it is 6 years.
She doesn't like having the same
No, because I want the actual rule. I'm feeling.
All right. Can I move down? Yep, anyone still copying?
Do we even get a rule for that?
We're about to get it. Okay, so we know that instead of just pressing, girls, instead of just pressing enter, 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 enter and counting how many times we've pressed enter, we know we can use a rule to find whatever term we want. Yep? We know that? Yes?
This is the A thing.
Okay, so when we are using growth and decay with geometric sequences, our rule is r to the n times v0. And v0 is our initial value, so what we are starting with before we've done anything to it.
Is it always a V?
Yeah, usually.
What's the big R?
The ratio.
Isn't that a small R?
Bigger, smaller. Put it in small r if you want. So r is the ratio. N is how many or what year or what term we want to find. Alright? If we are growing, our r must be bigger than 1. So our ratio must be bigger than 1, and if we're using decay, our r must be between 0 and 1. Really important, because otherwise your numbers will go the wrong way. So if we're talking about decaying, our numbers should be getting smaller. If we're talking about growing, our numbers should be getting bigger. If they're not, then you either need to put a 1 in front or you need to take the 1 away. Any questions about that? Cool, alright. So, the following recurrence relation can be used to model a compound interest investment of $1,000 paying interest at a rate of 10% per year. So our V0 is 1,000 and we've got 1.1 times Vn. Okay, use a rule to find the value of the investment after 15 years. So this is our rule. What does our R equal? Yep, 1.1, it says it right here. And what is our N? 15. I'm glad you're awake, Ava. And what is our V0? 1,000. So then we're just going to sub them into our equation. So we're going to be finding the 15th term. So we've got 1.1 to the power of 15 times 1,000. And what do we get? Nothing. Is that what we get? What do we get?
4,177.4.
0.25.
Yeah.
Any questions about that? Alright, we've got one more example and then you still can't nap, but we've got one more example.
Then we get to do AI.
We do.
So I was like, no, it's crazy, but it's like,
Is this one that long?
banging against the window. I'm like, as well.
Alright, can I move down, girls? Anyone still copying?
Okay, thank you.
Alright, I'm just going to rub that off. Okay, so last example. The following recurrence relation can be used to model a reducing balance depreciation of a car purchased for $18,500, where the value of the car depreciates in value at the rate of 10% per year. Who can spot the mistake in this? It's a typo. That I
Isn't
did.
it the same
Is it a
question as
math?
before?
No, it's not the same question as before because we're depreciating.
Okay.
Is it a math typo or like
It's very obvious.
Use a rule to find the
In
value
value.
of the investment after 12 years.
Oh, no, that makes
to the nearest dollar.
V0 equals 1000, Vn plus 1 equals 0.9 Vn. What have I done wrong?
Oh, you need to put V.
Take away.
V0
V and take away 1.
Keep going,
V0 equals 18,500.
Yep, excellent.
Not even that obvious.
Literally none of
Oh,
It was very obvious. What am I starting with? 18,500.
Literally none of us would have even second guessed that. We would have just.
I know.
Really important to check what's going on. Really
If you a
important.
rule though, it's their responsibility for it to be right. If
Yeah,
you
that
don't-
happens. Something like that happens in the exam, and you didn't check
Stuff
it.
like
and
that
you
always
just did it as a
Well,
result.
imagine if this was your answer from the one before.
Sorry,
Check
what?
your answers.
Wait, what? But that's happens. But it's still different.
No, it's important. It's not time consuming, it's important. Alright, use the rule. Girls, come on. Use a rule to find the value of the investment after 12 years, correct to the nearest dollar. So we're going to use our rule again. What is our R?
0.9.
Yep. Our N
12.
and our V0.
13.5.
18,500.
Yes, Liz.
Very fun. Alright, so we're finding the 12th term. We've got 0.9 as our ratio to the power of 12.
Wait,
Times-
is it a ratio or is it the recurrent?
It's the ratio. That's what we're multiplying by.
I thought that was like a difference.
No, the recurrence relation is just how we represent the data.
Okay, so we'll
R
have-
means ratio. What do we
we'll
multiply
have to
by?
calculate it. They always give it to us, don't they?
Yep. Alright, so put this into your calculator. 0.9 to the power of 12 times 18,500. What do we get?
5,224.95.
Oh.
Yep, and to the nearest dollar.
I know it's to the nearest dollar.
Okay, girls, there's lots of chatter. I know I've gone through the examples, but you still need to be listening to what's going on. Especially you girls in the middle row. Alright, so really important that you read the question. Correct to the nearest dollar. If you left your answer at this one, you would not get full marks. It is not to the nearest dollar. Okay, you need to make sure you round it correctly. So to the nearest dollar is to $5,225. Any questions? Alright, I'll give you
No, just do Fibonacci.